Let me first start. Um, I'm a professor at Rutgers University. Look in the center of the map with the red circle. In the center of the red circle is the state of New Jersey. Now look to the map in the upper left. New Jersey is the state. It's a small state, but in terms of population, it's actually one of the bigger states because we have on one side New York City, the biggest city in America, and on the other side, Philadelphia, the fifth biggest city in the United States. And I'm at what's labeled Rutgers, New Brunswick. That's the main campus. We're the eighth oldest university in the USA. In fact, we're older than the country. Rutgers was founded in 1766, and the United States declared independence from England in 1776. So you're all welcome to visit sometime, and I hope you do. Now, I'll introduce myself, but just quickly. I've been professor now 25 years, more than 25 years, and the whole time my major research has been system reliability modeling and optimization. Now that has evolved and changed, and what's meant by that has evolved and changed. You'll see today in the second half of my talk, primarily, some of my current work. Some of my collaborators are worth mentioning. Qianmei Feng is a graduate of Tsinghua, 2 degrees. And in fact, when Qianmei Feng, Professor Feng was an undergraduate at Tsinghua, one of her classmates was Kaibo Wang, who's now professor at the Tsinghua ISE, or IE, Industrial Engineering. Another very good collaborator, Xiaoyan Zhu, who's also a Tsinghua graduate, and now at UCAS, University Chinese Academy of Science. Xu Yangan is my last visiting researcher to America before COVID from Jiangsu, and of course, Professor Li. Let me move on. Now, this work in system reliability modeling and optimization consumes about 50% of my efforts still. The other 50%, which I will not talk about at all today, but is electrical power grid expansion models. And I've been doing this for about 15 years, and this all evolved from my work in reliability. In fact, I was contacted by the Canadian power company to ask if some of my reliability models applied to the electrical power grid, the transmission system. That's the part of the grid that basically goes into your home or your building or your school, the final portion. And my models did not apply, let me be clear, but it got me working on adapting and evolving those models such they did. After a while, we realized the work was so interesting, we took some of the reliability out of it, and we just simply looked on power grid optimization. I teach classes in linear optimization, nonlinear optimization, both for undergraduates and for graduate students. And if you're looking for interesting work in optimization, the energy field there's almost an unlimited amount of research efforts. Okay, quickly, and we'll get into the talk. My experience publishing, I have many research papers, as does Professor Lee. I'll just brag a little bit. In the journal IISE Transactions, they've computed that my H index, do you know what an H index is? You notice my H index is 64. That's pretty good. That's pretty good. Maybe not to the level of someone like Min Che or Enrico Zio, but they have many more collaborators. But that means I have 64 journal papers with 64 citations. If you just look at IISC Transactions, I actually have the highest of anyone. So that's good. And I have the most number of citations in a paper in reliability engineering system safety, and the fourth highest in IEEE Transactions on reliability. That's kind of interesting. At one point, it was the second highest. So you might think 2 other papers, and then it went from 3 to 4. You might think 2 other papers, passed it, but almost the opposite. Some of the very old journals, like from the I guess, 70s, 1970s and 60s. They had not been digitized yet. And when they digitized them, they found out a whole lot of new citations. Okay, and editorial experience, IEEE Transactions on Reliability, Journal of Risk and Reliability, IISE. And lately, I've done, as you can see here, quite a few special issues, and hopefully with Professor Lee, we'll be doing a new special issue starting very soon. But you see, I've worked with some of the world's experts on these special issues: Minche, Christophe Berger, Enrico Zio, Li Rongtui, some others. Oh, my experience at Tsinghua. So my first time to Tsinghua was 2008, 16 years ago. That was just my second time to China. Kaibo Wang invited me to give a seminar. Then 2014, also 2019, I've spoke at the IQR meeting several times. And then, as Professor Lee said, a visiting researcher. It was really great, but then, as we all know, the world changed in 2020. Now here, you look to the right, there I am 10 years ago, about ready to do an invited lecture. That's 2017. You see Min Che on the far left. Next to Professor Shi is Nozer Singh Parwala. You, probably the students in this class, don't know that name. He unfortunately died 2 years ago. He lived a good long life, but he was one of the true experts in reliability. 2019, this is my appointment as a Tsinghua visiting researcher. And then my last time to China before COVID, right here, I think that was, yeah, I'm sure that was my last time at Shenzhen. And you can see the back of Professor Lee's head in the front there. Now, my talk today. Okay, the first part of it is just, very simple review that you probably learned in your first lecture. So bear with me, just bear with me. Then at this point, I could take this talk many different directions. So this is a talk that I've labeled Advanced System Reliability Modeling. My current interest, not exclusively, but my current interest has to do with this issue of evaluating the basic assumptions we make in reliability and evaluating, are they really true, and can we depend on them? And if not, or if we mostly can, if not, when do they not hold? I know in reliability, when you teach new engineers, new students, often, and you're teaching how to compute a system reliability, not an individual component, but the whole system, there's often two basic assumptions that are made. One is homogeneous populations of failure times, usually, for the components. And another is independent failure times. And if you make those assumptions, you can construct a system reliability model. Now, let me say this. Most often, those assumptions are correct, or if not correct, an accurate approximation. But I'm kind of interested in when they are not. And so that's what you'll see for most of the second half of this talk, or even before that. So we start with the introduction. This is simple things I would describe to someone who doesn't even know what reliability is. Then we move to optimization with dependent reliability. And then we evolve to what my current interests are. System optimization with dependent degradation paths. And I review some of the work that's done, and I'll conclude with future research trends. Now, let me be clear, like I always do, I probably have more slides than I have time for. So if at some point I skip over a bunch of slides, well, that's how it usually goes with my talks, because I have many ideas. So let's start. Again, my first few slides, this is if your audience doesn't know anything about reliability. but I'm leading up to these assumptions we make. Now, first off, why do we study system reliability? And I'll use myself as an example. My undergraduate degree is at Cornell University in mechanical engineering. Cornell is probably, I don't know, I haven't seen the numbers, but maybe ranked in the top 5 for mechanical engineering in the US, maybe top 10 in the world, I'm not sure. So I'm very proud that I studied there, but I was never sure about mechanical engineering. But then my junior year, in America we say junior year, third year, I took a class in reliability, and just like you are right now. And for me, and maybe for some of you too, wow, it was what it was everything I wanted in an academic field. It involved some fairly advanced probability, it involved statistics, but it's also an engineering discipline. In other words, applied to real things. And then when you build it to the system level, it can be treated as an optimization problem. So once I was exposed to reliability, I'm not saying it's the only thing I wanted to do, but almost immediately I realized this is what I want to continue to work on. And Professor Lee Phoenix, who taught me that class my third year, he convinced me to take a graduate level class. And I'm just, 20, 21 years old, kind of scary because I'm in there with basically with men who are much older than me. But then that propelled, and then I have 2 master's degrees, but one is in industrial engineering with a PhD in industrial engineering too. So system reliability analysis, you're taking as a discipline. Hopefully, some of you at least, or maybe all of you will continue to study this. But it's necessary to measure and quantify reliability. Here's some slides I showed to sometimes I have to convince people to study this. Maybe you guys, you're in this class, but I want you to continue to learn. So look at you see the thumbs down? Thumbs down means reliability was not considered. So, here's this example, a nuclear submarine, very tragic, goes beneath the water, but the design never considered sufficiently the reliability aspects of this submarine, causing this huge tragedy with many deaths. Was reliability studied? Well, 1963, who knows, but most likely not. Another one, this is 1998, a train. Look at the train wheel right there. For whatever reason, that wheel was not designed to withstand the loads and stresses. Was reliability considered? See the thumbs down again. It was metal fatigue. That's a basic failure mechanism. Was reliability considered? I don't know, but certainly not sufficiently. So another thumbs down. And okay, I could go on and on. But if you're convincing people to study reliability, it's useful. Many, many tragedies. Now, 3 thumbs down. Is there any good examples? Thumbs up. AT&T, which in my lifetime, not in the last 20 years, but AT&T had a monopoly in the United States on phone service. Do you know, when I was a child, every phone was owned by AT&T. You didn't buy phones, you rented them from this company, AT&T. And very different than now. And they're all black. They're all the same color. But AT&T built this fiber optic cable. Now, this was at the time, something that was thought to be impossible. So they did study reliability, and they set a goal, a reliability target, 1 failure per 20 years, and they have surpassed that. Okay, thumbs up. This, I don't even know this. My student got this, but this is a company that prides itself on never having a field failure. Let's assume that's true. You know, maybe their definition of field failure is uh, is who knows what it is. But so of many examples, unfortunately, of not considering reliability. I could go on and on, but also many examples where reliability was studied, and more you see, strictly as technology evolves. Now, again, we're doing a historical look at things. So how do I study reliability? Well, I've categorized three different basic approaches. One, the traditional approach, and that's what I'm going to talk about at first. We collect data, usually on when items fail, with censored data as well. We take the data, we fit some form of a distribution, Weibull distribution, exponential distribution, log normal, something else. How do we fit that distribution? Well, I teach usually maximum likelihood estimation. Then you assume you have a homogeneous population. Now, is that a good assumption? I'm not going to talk about it in today's talk too much, but I could come back, talk to another talk. It's an approximation, but often not truly correct, because we may have a homogeneous set of hardware, but we don't have a homogeneous set of users who are stressing and operating these systems and components in different ways. And if we can quantitatively and numerically categorize the differences among these users, we don't need to assume homogeneous population. Nevertheless, and then we use probability models for system reliability. That's the traditional approach. That's what I'm going to start talking about. Now, we've evolved, however. There can be a physics of failure approach, where instead of collecting data, we study the physics and the engineering mechanics of how and when items degrade, and then how will they fail. These models are theoretically sound. They might be very useful designing a new component, but not practical always when at the system level, because many times these models are only known for the most critical components, and often, at least originally, they were deterministic, meaning it would compute a time to failure, but those of us studying industrial engineering, which I think is all of us, we understand uncertainty, and we understand that at best that's a mean value or expected value, and that we need to characterize the uncertainty. The final approach, and this is what I've based most of my research efforts on in the last few years, is degradation models. So instead of collecting data on when items fail or don't fail, we try to look at observable and measurable indications of a lack of performance prior to failure, and generally fit them with some form of a stochastic process, like a gamma process or a Wiener process, so that we can project and make projections of failure based on these degradation trends. Now, I'm going to talk about this at first, but then I'm going to evolve. But before we do that, let's compare degradation models to the traditional approach. Look at the graph down at the bottom here. We have 5 components under test. The star means it failed. The circle means it's censored. It did not fail, but we've stopped collecting data. The vertical dotted lines means I've inspected the system and I've observed whether it has failed or not. Now, under the traditional approach, I have 2 failures and 3 censored points. That's not enough to fit a distribution. However, if I'm looking at degradation trends, and I should add, if these are components that have observable and measurable lack of performance, and many components do not. Let me make that clear, but many do. Then I can collect data for all 5 components at each of those data collection points. And so instead of 2 observed failures, I have a lot of degradation data. Furthermore, if you look at the second bullet, I can use that for condition-based maintenance, where it's difficult to use the traditional approach to determine when to do maintenance prior to failure. You can do time-based preventive maintenance, but not justify that, but not so much condition-based maintenance. And finally, I can make so I'm going to model that degradation perhaps with a stochastic process, and I can make it a function of different stress covariates. Okay, quickly. System reliability. Remember, traditional approach. I've computed a distribution or a point estimate of reliability for each of these components, and I'm going to use probability models to estimate system reliability. Okay? Let's get the basics underway. If I have a series system, if I make an assumption of independent failure times, then I can multiply the component reliabilities. Sometimes I use a small r for the component, the big R for the whole system. Although you notice I'm not always consistent with that. What does a series system mean? Failure of any one component causes the system to fail. Parallel system, we see this expression here. Now, all components have to fail. So to derive that equation using basic probability models, instead of saying the probability that it did not fail, which is a reliability, you start the derivation with the probability that it does fail. And of course, the probability that it does fail for a parallel system requires all of them to fail. So very simply, you get this expression, 1 minus the product of 1 minus the reliability. Now, we can combine these two equations to get a series parallel system. When we do optimization, often we have structures that are series parallel or can be decomposed to series parallel. Now, I don't really like this diagram, even though I was the one who developed it, because it implies that every subsystem, I use the term subsystem for 1, 2, 3, up to S. It implies, by looking at it, that every subsystem has the same number of components, but of course, N1, N2, etc. Also, it implies that there's redundancy everywhere. In fact, for most systems, other than the most critical, mission critical or high reliability systems, in fact, for most systems, there's not that much redundancy. This implies there's lots of redundancy. In fact, for most operating systems, certainly for consumer goods that you use, your phone, your things around your apartment, there's probably no redundancy. But if it's a critical system, telecommunications, aviation, transportation, satellite, spacecraft. I saw China landed something on the moon. Well, then there will be redundancy. And it's often not, as this figure implies, the same everywhere. In fact, it's going to be where the required function is very critical. There'll be redundancy, and the less critical items may be none. Nevertheless, we have this equation. So we can construct the reliability for series parallel. We can construct the reliability of K out of N, where instead of a parallel system, we need K of those N functioning. Now, you can make this hard or you can make it easy. Let's make it easy so I can move on. If each of the components are the same, then it becomes pretty simple because I can use binomial distribution where any K out of N or K plus 1 out of N, etc. So if you look at the equation down at the bottom, you should recognize that as the sum of probability mass functions for a binomial distribution. K, N choose R. Right, or R would be the reliability. I should say R is something's wrong with that equation. Yeah, that should be N choose X where it says R. Need to fix that. What if it's more complex? Well, what we just need to do is to decompose into basic series parallel. Like, look at this more complex system. We see it starts as a series parallel, but then we have 2, 5, and 6. It's actually a parallel series structure, the opposite of series parallel. And then when we see 9, 10, 11, it's got this slightly more complex structure. So it's not a series or series parallel, but we can decompose it. What do I mean by that? We can group components together, use our basic equations for series parallel to construct the system. For example, 5 and 6 use series equation, 10 use parallel equation. Then I have a reliability for the two 10s. I can construct a composite or equivalent reliability there. Now it is series parallel when you consider the combined components and treat them as one. Now, many of you, well, I guess most of you, other than Professor Lee and others, don't know me, but I teach optimization. I teach linear optimization. I teach nonlinear optimization. This last semester at Rutgers, I taught undergraduate students linear optimization. I taught a master's level students an applied optimization class. These are students often from other engineering backgrounds, often working full time. They don't know anything. They don't know anything about optimization. Next semester, I'll be teaching linear optimization to the PhD students and master's students. So we have an optimization problem. You've been exposed to RAP, redundancy allocation. I'll talk about that. So here, I say example 1. I have this vector X. Vector X, it very generally is described as a design vector. What does that mean? It means the system architecture, the system structure, the choice of components which we're going to use. We have some objective function. I'm calling that Z1. It could be maximize reliability. If I'm dealing with the electrical power grid, it might be maximize system availability. Often, for our degradation work, it's minimize a cost rate. The word rate, R-A-T-E, implies some measure with time, cost per time, subject to some constraints, cost, performance, weight, volume, etc. Now notice this is example 1. This is design optimization. Example 2, maintenance optimization. Now, maintenance optimization, this implies this system structure is fixed. And what we're going to do is decide or solve an optimization problem. Again, very generally, a maintenance vector. What is that? Could be many things. When to inspect, when to replace a component. Do I replace a component before it fails or wait till it fails? Is there some condition I need to measure and replace the component when it reaches that condition? Am I measuring a RUL, a remaining useful life? And do I base maintenance on the RUL gets too small? So the maintenance vector could be many things, but the point is I'm deciding how to maintain it, not how to design it. Our objective function typically is going to be a cost rate, although it could be something else. And then we have constraints. So number 1, number 2, now example 3, before I show you, this is something both myself and I believe Professor Lee are very interested in. I know Xiaoyan Zhu from UCAS is also very interested. And that is combined design and maintenance optimization. Now, I'm not going to talk about that today, except for to the very end, and I probably won't have time for those slides. But but some future time, maybe Professor Lee will invite me to give a department seminar. This is one of my most important research topics I'm working on or I'm interested in. Combine now. Look at my objective function: z1x plus z2y conditional on x semicolon. What this means is my objective function is the cost to design plus the cost to maintain conditional or given that design vector x, but we can solve it all at once. So keep this thought in mind. Those of you who are PhD students, I believe it's most of you, lots of room for good research in this combined optimization problem. There's been thousands of papers written on design optimization, many by me and Professor Lee as well, on RAP and others. There's been thousands of papers written on maintenance optimization. There's been very few, but most of the maintenance optimization papers, not all, but the majority are on an individual component. But when you combine them to a complex system and combine the concepts of design optimization and maintenance optimization, that's some really good research areas. Now, quickly, just in that first group, and that's what I'm talking about today, the design optimization, the classes of problems can be reliability optimization. This is where the system structure is fixed, but I'm going to determine the optimal reliability values and then hope I can design or purchase components that have that reliability value. So I'm maximizing system reliability as a function of the reliability of the individual components. The individual component reliability, of course, is bounded theoretically between 0 and 1, or between some lower and upper bound. This would be a non-linear optimization problem. You have a non-linear objective function, non-linear constraints, but your decision variables are continuous. We can use gradient-based search, derivative-based search, to try to find the optimal solution. If the objective function is convex, and probably it will be, but I can't guarantee that, we can maybe get an optimal solution. But it's, well, depending on the nature of the nonlinearity, it's going to be a very difficult problem to solve. The next problem, which you should be familiar with, the RAP. Now, instead of determining the component reliability values, we're determining which components to use where the reliability values for those components are already known, which components to use, but also the architecture, how much redundancy to use, where. Now for this problem, we still have a nonlinear objective function. I say nonlinear or linear constraints. Often they are linear, but our decision variables are integer. Hard to solve. Hard to solve because gradient-based or derivative-based searches, don't work so well when we have integer variables. So and then particularly with the constraints, given that the optimal solution may not be where the partial derivatives are equal to 0, because that might be an infeasible solution. So this is a difficult problem to solve, which makes it interesting for researchers. Combine those, and you get the RRAP. Where I'm trying to both determine the system architecture and the reliability values. Now, realistically, you can determine the optimal reliability values, but that doesn't mean necessarily you can design a component or select one that has that. So it's a mathematically important problem. But probably, I'm going to guess Professor Lee agrees, but maybe not, the RAP would be the more practical problem to solve. Now, history lesson. Hope you like this. Don't know if you will. Now, I don't know you guys. I'm not sure if you know dynamic programming. If not, I can't teach you in a few minutes. But in my opinion, in the field of operations research, in the field of optimization, the most important discovery by far would be George Dantzig, who invented the simplex algorithm and linear programming or linear optimization. Now, what would be number two? Well, lots of people would have different opinions, but I would say this gentleman, Richard Bellman, he invented dynamic programming. Now, one thing that's curious, so this is 1954, they used the word programming. Dantzig, it's referred to as linear programming. Bellman, dynamic programming. Later, they called it stochastic programming for a different type of problem. Given that people like Dantzig and Bellman, they never used computers. All that was available at the time were large mainframe computers. So what did they even mean by programming? They didn't mean programming the way you and I use the word, write a computer program. They meant it in a much more general sense, in terms of a set of mathematical steps to solve a problem. So Bellman invented dynamic programming. Now, why am I telling you about this? When Bellman invented dynamic programming, almost the very first thing, the first topic he studied was reliability. So I view, for reliability optimization, Richard Bellman to be our pioneer. As far as I can tell, and maybe I'm wrong, but this is the first paper ever written on system reliability optimization. 1958, in the journal Operations Research by Richard Bellman and his colleague Stuart Dreyfus, who's also a famous guy. Now, again, what is dynamic programming? My guess is, and maybe everybody in here knows it, but I don't know that. And I certainly can't teach you dynamic programming in a few minutes, but I will give you exposure to it. Look at the animation. Hopefully you can see it move. I want to get from start to 7, but as you can see, I have different choices. Even from the beginning, I can go to 1, 2, or 3, and then maybe 4, 5, 6, and finally to 7. The little blue numbers in the circle, they tell me the time involved to get to there. So from start to 1 will take 4. The number inside the nodes tells me waiting time at the individual nodes. Now, for this problem, we could just try all possibilities and get the optimal solution. Sure, we could. But what if I wanted a mathematical way to determine the shortest path from start to 7? Well, see the red numbers inside the nodes? That tells me what's the shortest possible time to get to that node. Now, node 1, of course, there's only one way to get to it. So it's 9, 4 plus 5. Same with node 2, same with node 3. Now, when you get to 4, 5, 6, the important thing is you're doing a minimization of all paths leading into that node, but you only have to go back one stage. You only have to look back at the 9, 6, 4, and then how can I get there? Okay, this is still a small problem, but I can determine the shortest times to 4, 5, 6, 10, 9, 17, just by looking back one stage and then taking the minimum of the paths leading into it. Now, when I get to 7, here's the key point. I don't have to look back any further than 4, 5, 6. Doesn't matter to get my optimal time how I got to 4, 5, 6. I mean to optimize, just that I know the time to get there. Okay. And so finally, I can see I can get from start to 7 in 12 time units by going from 2 to 4 to 7. Okay. If you've never heard of dynamic programming, you still don't understand it. But how does it relate to reliability? Bellman, he says, well, I can treat system reliability just like the problem of going from start to 7. Now, you might be saying, why? It's completely different. Well, instead of going to 1, 2, 3, I'm going to design subsystem 1. And instead of taking the minimum of the paths leading into it, I'm going to take the minimum of all the different ways I can design it. I've defined this parameter beta. Beta says of the overall constraint capital C, and I'm maximizing reliability given a constraint on cost, of that capital C, if I use beta, which would be a number less than C, just for subsystem 1, how reliable can I make it? Well, I would add as much redundancy as I could. And that's what we see in the equation. I'm going to maximize. And so I'm going to increase x1, which is the number of redundant components, as high as I can. Okay, easy. Just like it was easy getting from start to 1, 2, 3. So I'm going to make subsystem 1 as reliable as I can. But keep in mind, beta is not known. Beta is a variable. So this is a function. F1 is a function of beta. Now, just like the next pass, if I want to design 1 and 2 together, now this time beta means of the overall cost constraint C, how much am I going to use for 1 and 2 combined? Well, look at the equation. I can fill up beta by adding to x2, but whatever I don't use, I can use for subsystem 1. So you see beta minus. So this is a function that calls itself at an earlier time. Now, when I move to 3, now beta will represent, it should be, the equation's a little bit wrong. It should be what I'm going to use for 1, 2, and 3 together. So I have two choices. I can use it for number 3. That's the left part within the max. Or use it for 1 and 2 together, beta minus C3. Anyways, what he found out finally is in the final stage, I don't use beta, I use the entire cost constraint, and I can optimize that. Okay, I enjoy telling that. Probably it wasn't clear, but this was the very first time reliability was solved. Since then, oh my gosh, linear programming, nonlinear programming, many. But to solve the most difficult problems, this was an important extension. But to solve the most difficult problems, at some point, we used evolutionary algorithms or a genetic algorithm. So I wrote the very first paper. Well, it was almost a tie. There was a paper by authors Payton and Campbell, published almost the exact same time. But mostly this is the paper that now has the 4th most citations in the journal IEEE Transactions on Reliability. So I wrote this paper with my PhD advisor, Alice Smith, who's now the editor. I think she's still the editor of Inform's Journal of Computing, to use the genetic algorithm. Now, personally, this is a terrible title. It's my title, but it's terrible. But it's because in 1996, just to use the GA, the genetic algorithm, to search this combinatorial nonlinear problem was viewed as somewhat interesting. Why do I say it's a terrible title? It doesn't explain why this is an important paper. It's an important paper because by using the GA, genetic algorithm, we could consider solution types that had never been considered before. What do I mean by that? Mixed redundancy types, mixing of different components within the same subsystem. The previous approaches, like dynamic programming, they restricted the solution form. So we were able to get better solutions. I remember I talked to, as a PhD student, my professor in linear optimization. I said, Professor Rashgopal, I can get solutions that are better than the previous best optimal solution. He looked at me like I'm an idiot because he teaches optimization. He says, David, you don't understand what optimal means. You can't get better than optimal. But then I explained to him that the previous methods restricted the types of solutions. So by introducing this paper, then people Enrico Zio, Gregory Levitin, Lu Dongxing, so many other researchers were able to solve more difficult problems. So let's skip ahead. Now, that's it. That's my review. So you understand redundancy allocation, how it's solved. Now, here's my interest. System optimization with dependent reliability. Wow, my real interest is coming. System optimization with dependent degradation paths, but one step at a time. Now, if you use the word dependence, let's say you use it in just your regular life, independent, not in school or academically. You'd say something, you have a friend who's dependable maybe, or you depend on your parents for money or something like that. We understand what that means. But in engineering, when we use the word dependence, it can mean different things. I started in mechanical engineering. If you told a mechanical engineer two component failures share a dependency relationship or dependent, they would think there's a very physical dependence. This causes this, cause and effect. This failed, causing this to fail. And that's a perfectly good interpretation, but it's only one. We can have economic dependence. A lot of the papers in industrial engineering have economic dependence. What does this mean? Two things, well, more than two. One, there's a constraint. If I repair one component, it might mean I cannot repair the other, even if it would be beneficial to do so. And then the reverse. I can repair or do preventive maintenance on two components at the same time, maybe not the optimal time, but it's actually going to save money because it will eliminate fixed costs. That would be economic dependence. Then, like the mechanical engineers think, and they're not wrong, functional or physical dependence. Look at the diagram on the right. That's a bridge. And you can see inside the bridge, those metal bars, those are rebars. The concrete cracks, causing the rebar to corrode. When the rebar corrodes, it increases the crack. Back and forth, physical dependence. Now, when I use the word dependence, I generally mean stochastic dependence. This means two components are failing, and their failure times have dependence relationship, and we would measure that with a covariance. If the covariance of failure times is 0, there is no dependence. If the covariance is positive, it would imply as one component fails, if it fails early, the other component may fail earlier too, in a probabilistic sense. If one component fails later, the other component may fail later, in a probabilistic sense. All of those models for parallel and series parallel assumed independence. Is that a good assumption? Yes, most often it is. Is it always a good assumption? No. And so I'm studying those instances where it's not. Now, why would there be dependence? Well, it could be, or why would there be stochastic dependence? Well, it could be because of functional or physical dependence, absolutely. But there may be a third variable that we don't even know about that is influencing both of them. Perhaps something in the atmosphere, some contamination, pollution. We may not even realize it's there, or we might realize it, but we can't measure it, but it's influencing both of them. Furthermore, if you look at a complex system, unless it's very large, the components are in a close physical proximity. They're close to each other. So they're being exposed to similar environmental and usage stresses. For example, two cars are produced, they're the same. One of them, the driver is in the desert. One is in a tropical forest. They're being exposed to different sets of stresses. And all the components in the desert are sharing the same stress profile, all the ones in the forest also. So even though the one component might not be causing the other one to fail, they may all fail early in one instance or all fail late. Okay, so this is what we mean by dependence. Here's an example. This is Monte Carlo simulation. Look at the graph in the upper left. These are components that are degrading with time. We have a probability density function. When you see those degradation paths reach the threshold, it's a failure. There's a distribution of those failures. This is just a simulation. I'm going to say there's two components in parallel, 1, 2. They both have normal distributions of failure time. One has a mean of 200. One has a mean of 220. They both have a variance of 20 squared, the variance of failure time. But the covariance, I'm going to change. Now, as I change the covariance, I'm not changing the variance. Okay, the variance stays the same, but I'm going to introduce a covariance. Now look at the graphs. Covariance is 0. This is a graph of T1 versus T2. No pattern. I've increased the covariance. Well, you could certainly see a pattern, but it's mostly because of that one point in the upper right. This is Monte Carlo simulation. Failure 1, failure 2. Let's increase the covariance. I also have computed the correlation. So we see the covariance has gone from 1 to 12 squared to 16 squared. Correlation 0.64. One more time. Probably not realistic, but just to see mathematically. Or correlation of 0.9. So here, what we're seeing, the left, they're independent essentially. The right, obviously, they're not independent. Now again, this doesn't mean component 1 failure causes number 2 or the reverse, although it could be. It simply means that there's some relationship between them. If one of them tends to be low, the other one does as well. Now, our models often ignore that. Do we care? Well, yeah. If I have a parallel system, so what we have here, the equation on the left, that's the equation if we assume independence for a parallel structure. On the far right, we see the maximum reliability. Again, because of a parallel structure, that's as low as it can be, right? Because whichever one is highest, and then we got the other ones to provide protection. So it's going to be higher than the maximum. In the middle, we see the actual reliability. So what we're saying is for a parallel structure, the real reliability is less than what we would predict or what we would compute using our probability equations based on independence. Why is it less? It's really easy to explain. Let's say there's no failures, but when the first one fails, if they're independent, you've got protection from 2, 3, and 4, or whichever ones it is. But if there's dependency, if the first one fails, all of them perhaps are going to fail very soon after, and you lose the protection. Now, harder to explain, and I'm not going to do it today, but I could, for series. Now, the equation on the left, the product of the different component reliabilities. The upper bound for series is the minimum reliability. You know, that's you know, so in America, we say a chain is only as strong as its weakest link. A system is only as reliable as its least reliable component, a series system. But the actual reliability is in between. So actually, the actual reliability, considering dependence, if there is dependence, is higher than what you would assume with the probability. So is it pessimistic or optimistic? Well, can't say. Sometimes optimistic, sometimes pessimistic. Now, if I'm going to optimize system design, look at my formulation, trying to maximize reliability, given this design vector X. I have constraints. To solve this problem, we generally compute reliability assuming independent time to failures. Okay, let's say we do that. Let's say we get the solution in the upper right. But what if we assume independence, but they're really dependent? What you're going to see is you're going to use more reliable components and less redundancy. So here I made the size of the component to mean how reliable it is. And so here's the issue. If I do have a dependency relationship, I want a system like on the bottom. But to solve the problem, I may need to assume independence, and I'll get a solution like the one on the top. Ah, that's my research interest. Now, what are some examples of dependency? Here's one, because it's written by me, and it's easy to explain. Do you understand the concept of common cause failures? Common cause failures means components are operating and failing, but occasionally something will happen and it will trigger several simultaneous components, maybe all components. So look at my diagram. See, we got components 1, 2, 3. The little explosion means failure. Oh, number 3 failed. Okay, let's fix it. Oh, number 1 failed. 3 again. Ah, common cause failure. They all failed. 3 again. 1, 3, 3, 1. Bam, another common cause failures. Now, if you think about it, the presence of these common cause failures introduces a dependency. Why? Because occasionally, when the common cause failure occurs, all the components will have a failure time that's the same, or the ones that have not failed yet. So to test this, what I'm doing, I'm saying the 3 components, 1, 2, 3, fail independently, but there's a common cause event occurring. The common cause event I'm labeling lambda CC. My graphs, T1 versus T2, T1 versus T3, T2 versus T3, Monte Carlo simulation. You look at each of the components have different Weibull distributions, but I'm going to start increasing lambda CC. Right now, lambda CC, 1 over 150. Exponential distribution. Now we're going to increase it. 1 over 130. Is there a pattern? Not really. Look, I don't see one. Increase it again. Well, you see it on T1 versus T2. And now why do you see it for T1 versus T2? Because they have they fail first. And actually, I'm not sure. I'm not sure. I don't see, I guess you do see it on T1 versus T3. Not so much T2, T3. So let's increase lambda again. Doesn't actually look much different. Again. And again. Now we see it. Now, what does it mean, the points along the diagonal? That means a common cause failure triggered both components to fail at the same time. So we're seeing some dependence. This is from an old paper written by myself and Jose Ramirez Marquez, who's a professor at Stevens Institute of Technology. I recall Jose visited Tsinghua in 2000, I don't know when, but I was there too, probably 2019. And I think I don't know, but maybe the first paper written on system optimization with common cause failures. Here's another example of dependence. I'm just trying to give you some practical examples. Do you know the concept of load sharing? if you have learned about load sharing, often they use this elevator as an example. See on the left, that's an elevator car held up by 3 cables. Look at my diagram. Oh, there's a failure. If one cable fails, the elevator car will be held up by the other 2. Well, that increases the load on the other 2. So their failure times will decrease probabilistically. Another failure. That cable in the center is carrying all the load. So here's how we're going to model this. We're going to say all 3 components have Weibull distributions for failure time. But now look in the center of this graph. As one failure occurs, it doesn't matter which one, the Weibull scale parameter is going to decrease by a factor alpha. When 2 failures occurs, it decreases by alpha again. So basically, the scale parameter is not the mean time to failure, but it's kind of like that. So as one fails, the mean failure time of the other 2 is going to decrease by alpha. Makes sense. But now let's vary alpha. Alpha is 0.1. Again, here's a graph of T1 versus T2, T1, T3, T2, T3. Alpha is 0.1. Do you see a pattern? I don't. Let's increase alpha. Again, when we increase alpha, that means when one failure occurs, the failure times of the other 2 are going to decrease a lot. That's going to introduce a dependency relationship. Why? Because as alpha gets high, when one failure occurs, the other ones will fail soon after. Alpha 0.3, you see a pattern? Little, not too much. 0.5, you definitely see a pattern. 0.7, probably not realistic to have it so high, but maybe. And of course, you see a complete pattern. Dependence. So what if I want to optimize the system with load sharing? So let's do this quickly. If I'm going to solve this problem, I need a model for system reliability given dependency. I showed you common cause and load sharing just because I think they're easy to understand. I'm not really personally all that interested in them, although I did write that paper on common cause. What's another one? Markov chains. Let's say I had these 3 components. I'm assuming all of you have learned Markov chains. If not, you can just skip this. It's just one slide. I have 3 components, and look at the states on the Markov chain. Each state is a 0, 1 for all 3 components. 1 means it has failed. And if you look at those transition rates, lambda, they start to increase. So when one failure occurs, the lambda will increase for the other 2. And again, just like load sharing, as one failure occurs, if the lambda increases by enough, the other ones will fail shortly after. For this system of 1, 2, and 3, the way it's arranged, the states in yellow mean system failure. So I could introduce this dependency relationship with Markov chains, but if we're solving optimization, unless it's a small system, this would be hard to do. This would be hard to do. Plus, I would have to quantify all these transition rates. But obviously, Markov chains is an excellent way to study any type of reliability system. Now, could I have a joint distribution function for the failure times? So let's be clear here what I'm talking about. Let's say we have a Weibull distribution or a log normal or anything else. If they're independent, the joint distribution function is just the product of the individual probability density functions. However, if they're not independent, I may need a multivariate probability density function. So I've shown an example here, a bivariate normal distribution, 2 components, and with a normal distributed, but a multivariate normal with a correlation. All right, there it is. Here's another example, bivariate Birnbaum-Saunders. Okay, now let's be realistic. Oh, and you see the lower right, the system reliability. I'm simply going to integrate that joint distribution function. Now let's be realistic. This is already complicated for two components. What if I have many components? And what if it's an optimization problem where I don't know the number of components in the optimal solution? So theoretically, this is correct, certainly correct. Practically, it might be difficult to do. And how am I going to quantify those? So let's move on. Coppola function. Now, what is a coppola function? Coppola function is when you have a dependence relationship and you're going to approximate the joint distribution function based on the marginal distributions of the individual components. So this is what I want to emphasize. If you don't know a coppola function, this is my introduction of it to you. So you look at the first equation. I have f of capital T, T1, T2, T3, the joint multivariate probability density function for 3 failure times. In practice, it may be some complex theoretical distribution, but I'm going to approximate it with a coppola function. Notice in this example, it's the product of the individual marginal probability density functions multiplied by this coppola function, T1, T2, T3. This is just one example. Then I can compute the reliability for integrating that joint distribution function from T to infinity in all dimensions. Now, what is a coppola function? What are they? Well, there's many different choices. Look at the diagrams on the right. Now, if it was independent, it would be circles. It would be circles. But here, this shows dependency relationship. As one random variable is low, the other one is low. When I gave a talk, or my student gave a talk several weeks ago at IISE, Min Shea asked a question, as he always does. He says, what if there's negative correlation? And we hadn't considered that, although we will now. We will now. So we have this coppola function. Looking now to the equation on the left, we have the joint distribution function, but we're approximating that. We don't know it. We're approximating it with the coppola function. And here in this example, we have the cumulative distribution functions, the marginal cumulative distribution functions. Okay. Some other examples. Now, let's actually do this. Have a series parallel system. We're going to assume a dependency relationship. So here, the reliability of this subsystem I, 1 minus the coppola function, is a function of the marginal cumulative distribution function, 1 minus R. So we have reliability. We have 1 minus R, which is the CDF, cumulative distribution function. And we have a coppola function. The system. Now, I can have a survival coppola function. So instead of, as a function of the individual subsystem reliabilities. Let's solve an example. Components in subsystem is a very simple example, but it's the only one we've solved so far. Subsystem 1 and 2, exponential failure time. Subsystem 3 and 4 have a gamma degradation process, linear. We're going to assume here the subsystems are in fact independent, but the components within each subsystem have a dependency relationship. Here's the paper that's written. This is dated May 2024. In other words, last month. This is a paper from IISE IISE conference. that was held in Montreal last month. My student Jen Hong Lee presented this paper. Now, I think I'm missing a slide or they're out of order, but that's okay. I need to move on. We see here the objective function given the, my slides are out of order, apologize. We're using the Clayton cupola here. We've just made this assumption. And one of the reasons we've made this assumption is the Clayton cupola has one variable. That doesn't mean it's correct, theta. And I can vary theta. As theta is low, there's less dependence. As theta is high, there's more. Look at the graph on the left. This is variable 1 versus variable 2. Now, for us, this will be reliability between 0 and 1. When theta is 1, really very little pattern, but as theta increases, the dependency relationship becomes very clear. Now, given this cupola function, I can now consider the dependency. Now, these are two graphs, subsystem 1, subsystem 3. We've fixed it at 3 components, but we've increased the theta. It's the same components, but the dependency relationship is increasing. As theta increases, the reliability decreases. Okay, this is what's going to allow us to study. Now I'm going to go back, slides are out of order. So now I'm going to solve this optimization problem. It's very simple. For each of the 4 subsystems, I have 1 component choice. So I'm just going to decide on redundancy level. Notice in the lower right, cost and weight. Notice component 4 costs much more than the rest. Now, I have a very nonlinear objective function. I have integer decision variables. I'm going to solve with a genetic algorithm, so it's not guaranteed for optimality. But for a small problem like this, relatively small, it probably will converge to optimality, but I can't prove it. But I'm increasing theta. Now, what does that mean? As the dependency relationship increases, the system reliability goes down. Now, keep in mind, we assume no dependence among subsystems. If we did that, it wouldn't necessarily go down, but it would change. But what else do we notice? The system structure changes. Now, subsystem 4, because it was so expensive, it never uses more than 1. But we see the system structure changes. Now, are these optimal solutions? I don't know. Let's solve it now with nonlinear search, gradient-based search. Problem with gradient-based search, of course, is it won't converge to an integer, but it will give us a lower bound, or excuse me, an upper bound on system reliability. So we'll look at these numbers. How close are they? Well, I would say not that close, really. But again, the gradient search or nonlinear search is not going to an integer solution. So that does not mean the GA is not optimal, but it does provide an upper bound. So if it's not optimal, it can't be any higher than those numbers on the bottom. Okay, let me look at the time. 8:20, like I knew. I plan to go 2 hours. I'm hoping that's about right, Professor Lee. Now, I'll need to move faster. System optimization with dependent degradation paths. If you continue to meet with me over the next few years, won't be the only thing I'm working on, but I'll often be talking about this. Now, I'm going to have to do this somewhat quickly. I want to get to where my most interest is. I have a kind of a lengthy review, which really we don't have time for. First off, what do I mean by degradation? The traditional approach, we collected times to failure, and it fit a distribution. So an item had not failed, and then it has failed. So it's like 0, 1. When we study degradation trends, look at this graph here. Each of the dotted lines is a degradation path. Notice they're not all the same. They're random. We see a vertical line labeled failure threshold. Now we see those three things that look like normal distributions. Now tilt them up in your mind so they're facing you. And what they are is for fixed points in time, those are the distribution. I've drawn them to look normal, but they could be anything. I've also drawn them so that the variance is increasing. Now it could be often staying the same, but here I've shown it so it's increasing. So when the individual degradation paths hit or reach the failure threshold, that's a failure. So then we can construct the failure time distribution. Now, the benefit of degradation is I can collect the data and establish the trend without observing any failures. I credit this guy, William Meeker. I think if I talk to, he goes by Bill. Often people in America named William refer to themselves as Bill. Actually, for people like my age, everyone uses a shortened version of their name. For example, my first name is David. I go by Dave. Anyways, Meeker he's also from, I'm from the middle part of New York State when I was a child. Bill is also. Anyways, he's been a professor at Iowa State since 1975. Now, I just read recently, so that's, what year are we in now? So that's 50 years, essentially, almost. I read recently he is finally retiring. Now, in America, there is no retirement age. You can keep working as long as you're alive, and many professors do. And so he's been working there for a long time. And he wrote, in my mind, the first paper. I don't know if it was the first paper, but the first paper that received credit. In other words, was recognized as an advancement. I asked him once, how did you think of this? How did you think of this? And he said he was working at Bell Labs, and that's actually, I talked about AT&T before. Bell Labs was part of AT&T. And he said they asked him to compute failure distributions on items that never failed. These were lasers. And he didn't, he told them it's impossible, but they told him they needed an answer. And so it was, anyways. Now, he wrote his first paper, and I would say for about 15 years, other than a few statisticians, hardly anybody read it. It often goes that way. But finally, somebody did. And finally, some engineers did. Now, what do I mean by degradation? There's some, listen carefully, observable and measurable lack of performance. How often is that true? Well, oh, that's my student, Jianhong Li. He's from Chengdu. These are these steel rebars that go in bridges. We can see on the right, they've degraded. Metal fatigues. We have wear of moving and rubbing surfaces. Okay, and many others. Now, how can I model these? I mostly want to focus on gamma process and Wiener process, but let's start with Meeker and Liu, his student Liu. Meeker and Liu's original paper. This has different names. I call it a random effects model or a general path model. We see Xij. There's some function, but this function or the degradation path has two vectors, and these are random vectors. Now, in theory, they're vectors, but there could just be one value. Notice vector phi, bold phi, that's for all units, but it's random. So it's going to create the distribution. And then we have vector theta I. That's just for component I. That's, I don't mean component I, for unit I, the individual item I. That's random too. And so the randomness of those two vectors creates the random path. Now, mathematically, often we assume this function is linear. This is pretty easy to solve. Now, here's some examples. What's the problem here? Well, in one sense, none. But the problem is if I look at the distribution of those straight lines, it looks pretty good. But I am actually assuming each line is straight, which of course is not realistic. But nevertheless, that's the model. Now, what I normally use in my research is a gamma process. Why? A gamma process is monotonic, meaning it doesn't get better by itself. For mechanical items, that's a good assumption. If we're studying the human body, it's not a good assumption. If we're studying electronics, it's not a good assumption because the signal will improve. Sometimes we don't know why. But for many mechanical items, they wear out, fatigue, corrosion. It's a monotonic degradation process. Now, let's get our terms clear. We can have a gamma process, a gamma distribution, a gamma function. They're three different things. A gamma function is just a function defined as capital gamma, you can see down below. What's a gamma distribution? It's a probability density function. It's a random probability density function of a non-negative random variable. What's a gamma process? It's a stochastic process that given any two time intervals, T1 and T2, the change in degradation is a gamma distribution, but of course as a function of T1, T2. Now T1 can be 0, which is very useful. So the mean can be linear. You see the graph here of a linear gamma process, but it can be nonlinear too. It can be nonlinear too. So gamma process, monotonic. A Wiener process, not monotonic. Here, look at the equation. We have some drift parameter mu, so it's getting worse with time. But then we have diffusion parameter sigma, where capital W is a Brownian motion term, randomly varied between 0 and 1. Here's a graph of 4 different Wiener processes versus time. Look at the red graph. The red graph, or the red line, has gone above the threshold, but then goes below it. So now, instead of just computing the probability we're above the threshold or below the threshold, we have to worry about the first hitting time. So it creates a different problem. Oh, and the Wiener process in an increment can have negative degradation, although the overall trend will be positive. Notice, sees H but goes below. I won't talk about it, the inverse Gaussian. There's a very productive and excellent researcher in Singapore, Zhisheng. Apologize, I can't say the Chinese names correctly. You know, I don't know if you guys realize there's certain sounds in the Chinese language that we just don't have in English. And so no matter how hard I practice, I won't be able to say them. But Zhisheng has written a lot of excellent papers using inverse Gaussian and kind of popularized it. Now, I'm going to keep looking at the clock. Last year, we wrote this paper. So November 2023, so just 6 months ago. Dependent failure behavior modeling for risk and reliability, a systematic and critical literature review. I recommend this paper. The first author, Jiguo Zhang, someone who Professor Lee knows very well, and Barros from France, and myself. Jiguo lives in France now too, both Jiguo and Anne, or An in French they say, or I should say Professor Barros, are professors at Central Supalik, which is part of the University of Paris-Saclay, which Professor Yanfu Li also was affiliated with. We have this paper of a very thorough literature review. If any of you happen to know Jiguo Zhang or happen to meet him, please mention I give him most of the credit for this paper because he deserves it. In this paper, we look at all different ways, again, it's a literature review, of modeling dependency. And, I don't have time here. I'll just leave you to read this paper. But you look at the diagram on the left, we can have mechanical models, which we're not really looking at here, versus statistical dependency models. And we can have lifetime distributions. That's what I talked about earlier today. System state, this would be more the Markov chains and things. But then degradation process, that's what I'm talking about now. How do I model it? Again, I'll skip over it. I could use Markov chains, obviously an excellent method to use, but for optimization, maybe not so practical, at least for a big system. Other approaches as well. I'll run out of time, but as we're moving to the future, machine learning type approaches. Markov chains, look, Markov chains are applicable. Now let's say component 1 and 2 have 3 different states, 1, 2, 3. I can then model as each component goes through these different states, if the transition rates increase, let's say the transition rate for component 2 increases when component 1 degrades, it will create this dependency relationship. Sure, great approach. If I've got a fixed system design and there's not too many components, excellent approach. Many good papers have been written. Don't want to discredit them one bit. But for the type of work I do on optimization, maybe not the approach I'm going to take. Shared shock models. Let me skip over this. I have quite a few slides here, mostly because it's work done by me. This is work by me and Shenmei Feng and Hao Pong. Both Feng and Pong are Tsinghua graduates. This is 10 years ago. Shared shock exposure models extended to system level. Also with Sanling Song, my former PhD student. Let's try to do this quickly. I've got a system. Now watch the diagram. If you're falling asleep, wake up and watch. Now let's do that again. Now, all the components are degrading. Then every once in a while, the shock hits. Now notice something very important. Let's do it one more time. The shock isn't hitting individual components. It's hitting the whole system. So when the shock hits, every component feels a jolt. Every component experiences an incremental increase in their degradation. So as the number of shocks or the rate at which shocks occurs increases, it will create a dependency relationship. Let me try to explain. The number of shocks will be random. It's a random variable. And so randomly, sometimes it's high, sometimes it's low, according to a distribution, Poisson distribution. If the number of shocks is high, all of the components will experience more shocks. All of them will have more of these incremental increases due to the shock damage. If the number of shocks is low, probabilistically, the reverse, creating this dependency relationship. This is just one component. Look at the diagram. It can fail due to a soft failure. It can fail due to a hard failure. I hate these terms, soft and hard. I did not invent them. A soft failure simply means the degradation has exceeded the threshold. A hard failure means it failed suddenly because the shock itself was too severe. But please notice the vertical dotted lines, tau, 2 tau, 3 tau. I'm sorry, I misspoke. Notice on the x-axis, T1, T2, T3, and then look up. When shock T1 occurs, the shock magnitude is W1, but there's this incremental damage, Y1. This is for every component. For that component to survive, it has to have no hard, no soft, but the presence of the shocks increases the likelihood of both, creating the dependence. Quickly, look at the first equation. Notice because they are not independent, I cannot multiply the component reliabilities. I'm sorry, yeah. So for component 1 to survive, look at the equation. W is the shocks, X is the degradation amount, including the incremental damage. Component 1 has to survive all the shocks, plus the incremental and damage, or the degradation, has to be less than its threshold. Now, how am I going to solve this? It's actually, I mean, the mathematics looks hard, but it's not. The trick I always use, conditioning. Let's condition on the number of shocks. And if I condition on the number of shocks, I can then sum on the number of shocks. And for a fixed number of shocks, the probability of a hard failure and soft failure becomes, now listen carefully, conditionally independent. They're only independent because I've conditioned on the number of shocks. If the number of shocks is fixed, then they become independent and I can solve it. And that right there in blue, that's, in my opinion, the most important equation in this paper. That's the reliability of this system. Now, on the left, in the first red circle, that's just a cumulative distribution function raised up to m, where m is the number of shocks. Easy. On the right circle, I had to use a convolution integral. That's what you see there. I'm integrating over the random sum of the number of shocks. Probably did not explain that, but it's in the paper, and that's in the blue box, one of the main contributions of this paper. Now, Nushin Yousefi in 2019, we extended this paper to an optimization paper to determine, look at the diagram. Now, why do I have that moving? Because the on-condition threshold becomes a decision variable in my maintenance optimization problem. Remember way back, that's part of vector Y. Now, I very much would hope you to read this paper. Unfortunately, there's an error in the example table, the data in the example. You know, whenever an error occurs in one of your papers, it's terrible, but it happens. No problem with the mathematics. Mathematics are all correct, but the data table has a mistake in it for the example. Hate to admit it, but I got to be honest. Now, system optimization dependent degradation paths. Can I have a joint distribution function, not on failure time, but on degradation amount at time t? Very difficult, but here's an example. This is an example, 3 students, and I don't know handy, I'll bet Professor Lee probably does, but the other 3 students all got PhDs with Min Shea, either in Singapore or Hong Kong, I'm not sure. Very simple paper, but very important paper. Not sure they even realize. They have 2 components, but 3 gamma processes, Y1, Y2, YU. But each component, X1, X2, look at the lower equations, share one of the 3 gamma processes. So as that gamma process gets big in comparison to the other two, there's going to be more of a dependence relationship. And if it gets small, now we can solve this. We can actually determine theoretically the joint distribution function. It's not hard to do. So the joint distribution function, I simply need to condition and integrate on the y0 term. So there it is. My student Zhenhong Li, we're going to extend this paper to n components. We're working on it right now. We're almost done. It's a direct extension, but I think it should be published. Maybe just go to a conference, but I hope to a journal where we can have n components. And I'll talk about it later if I have time, which I probably will not. Okay, quickly. When you look at this issue of dependent degradation paths, you'll see one name over and over again. There's Yili Hong, a statistical professor at Virginia Tech University. You see Jisheng Yi gets his name. He tends to show up on a lot of papers. I don't know how. And this is, by the way, Yili Hong received his PhD with William Meeker as his PhD advisor. So of course, he's going to be extending some Meeker's work. He has a general path model, just like Meeker. But he's got this parameter omega, it's a vector. And this vector follows a multivariate normal distribution. Now, Y is for ijk. Oh, I'm forgetting now. It's for time k, component I, individual unit j. Or I may have the I and j reversed, I apologize. But this creates, because omega is multivariate normal with a covariance, the path becomes also a distribution. Hong, then, this is 2021. He wrote another paper where he said, well, instead of multivariate normal, let's use Coppola function. All right, let's move on. Random effect stochastic processes. What's that? I have a stochastic process. Each component has a stochastic process, typically with a number of parameters. Gamma process has 2 parameters. A Wiener process, typically 2 parameters. But the parameters themselves can be a random variable. And if the parameters are a random variable, that's a random effects stochastic process. Now, the random variables can be shared among components, creating a dependence relationship. This is a very simple paper. And when I use the word simple, that's not an insult. In fact, if you can write a simple paper and yet make a breakthrough, that's better than a complicated paper. This is a simple paper. Bivariate Wiener distribution process. Now, again, they limited themselves. They didn't have to. They only have 2 components. They both have a Wiener process. But look at the equation. There's this term alpha. Now, subscript S is for S equals 1, component 1, S equals 2, component 2. If you ignore alpha, they've got a drift parameter or drift function here, H. They've got a diffusion parameter, sigma, and the Brownian motion term, B. But alpha does not have a subscript, and alpha is normally distributed. So as alpha becomes high, the drift term for both components becomes high. Now, we wrote a paper, 2020. To be honest, I hadn't seen this paper, but I realized later it's a very similar idea. And that's this paper. This is 2020, reliability analysis of systems considering clusters of dependent degrading components. Nushin Yousefi, myself, Sanling Song. Nushin Yousefi now works machine learning for Amazon. This was part of her PhD dissertation. Now here we have clusters of components. Now, don't get confused. We have 4 components and 2 clusters. If 2 components are in a cluster, that does not mean their degradation is similar or the same. It could be, and in fact often is. But what it means is they increase and decrease together. These are 4 simulation runs of the same 4 components. Look at blue and orange. On the left, blue and orange are low like the other 2. On the far right, blue and orange increase. But notice, blue and orange are always together. That's what we mean by a cluster. Blue could be high, orange could be low, and it could still be a cluster if they were increasing together. So this is what we mean by a cluster. And so we wrote this paper, Systems with Clusters of Degrading Components. I say number 1, because now we're writing number 2 right now. So how we do this is also a random effects gamma process. But we have this one parameter, theta I. And theta I, so that's going to be the scale parameter for component I. But instead of a fixed parameter, it's a function. It's a function of these individual thetas, which are random variables. And there's 1 theta for each cluster. Now, realistically, how many clusters will there be? Usually 0, so don't read my paper. And if there are clusters, probably 1, maybe 2. When Nushin Yousefi wrote this paper, she limited it to 2, and it was all done. And then I said, because I'm an academic and I'm a researcher, I say, why 2? Why can't it be K? So we rewrote the whole paper with K clusters, where K is to be determined, but the equations got so much more complicated, I now think it was a mistake. We should have left it with 2, but I still recommend this paper. So I can use this. I don't really show it, but I can write a reliability expression for the system with clusters. I can use that as my objective function in optimization. This is number 2. Notice I say 2025. This is a direct extension of the Bin Liu paper. Bin Liu is a professor in Scotland now with a PhD, Hong Kong, I believe. City University of Hong Kong, maybe Singapore. No, whatever. And this is a direct extension. Maybe I'll ask Professor Liu to be a co-author. His paper had 2 components and 1 common term. Here we're going to have n components, each with an individual gamma process, but m common terms, where m in this model would represent clusters. Now, just like we showed before, by conditioning on the W terms, I can determine reliability expressions. It's not too difficult. And here's an example. We kept this pretty easy. Let me skip over. Although I did want to show this, we had these 4 simulations and we increase the dependence. Look at the graphs. On the left, okay, look at the equations. I've kept this alpha. As alpha is low, so here we have W1, W2, so 2 clusters. But each component has its individual gamma process. When alpha is low, there's going to be very little dependence. When alpha is high, a lot. So look at the graph. Alpha is 0.1 on the left and 5 on the right. Now I'm going to do 4 different simulation runs. First, watch the graph on the left. No pattern, right? There's just 4 curves. Now, look at the one on the right. Notice sometimes sometimes blue and orange are on the top, usually, but sometimes they're on the bottom, but they're always together. That's what we mean by a cluster. Now, the example on the right is too extreme. It's not realistic. So now look at the one on the second to the right. See, here red's by itself, but overall, red sticks with green. Okay, this is a paper we're almost finished, has not been submitted. So how do I pick the clusters? You can look at the paper. Let's look ahead. Now, in December of 2019, we had a special issue in reliability engineering system safety, myself and Enrico Zio, RAMS optimization. The very first paper in this special issue was written by myself and Enrico Zio, The Evolution of System Reliability Optimization. We use the word evolution just like evolution of species, from monkeys and apes to humans. Except for we're not talking about evolution of species, we're talking about evolution of research, from Bellman's dynamic programming to multi-state to mixed redundancies to degradation paths. But then look into the future. And so as we look into the future, we make some recommendations. And in this paper, which is already 5 years old, but here's what we say, 1, 2, 3. This is a good way for me to end my talks. 1, all the models you've seen today are static. What's that mean? We solve them once and we act like we're done, but we're not. Models, as we look to the future, cannot be static or should not be static. They should be dynamic. So what do I mean by dynamic? Changing with time. Read number 1. Dynamic models respond to changing environment, usage profiles, failure trends. Data is collected, processed continually, models re-optimized to determine maintenance plans, design change recommendations. How are we going to do this? Machine learning, among others. 2, don't assume homogeneous populations. System optimization for fleet of systems are customized, even dynamically. Let's just focus on 1, 2. System reliability assessments driven by field data, machine learning, reinforcement learning. Here's another special issue, came out, I think it was last year, with Ping-Fong Wang and myself, mostly Ping-Fong Wang, physics-informed machine learning for reliability and safety. Machine learning models, I want to emphasize one paper, a paper from last year with Mihaela Matisse. If you don't know that name, you should see it more. She's a professor in the Netherlands. Also Jiguo Zheng again, and Anne Barros from France. And I'm going to end soon, but dynamic predictive maintenance using probabilistic data-driven prognostics. Here, our measure is RUL, remaining useful life, or sometimes I say residual useful life. And our model becomes dynamic using machine learning. We're collecting new data, we're updating that RUL, essentially in the limit at all times. And our design recommendations are based on that dynamic updated model. I got a few more slides, so I'm trying to finish after 2 hours. This isn't new anymore, but this is a good example. This is a colleague and a friend of both Professor Lee and myself, Ajit Parlakad. from Cambridge University. The first author is Hao Li, who's also a graduate of Tsinghua. And she lives in Beijing now, but she doesn't work in academia. Last I heard, works for McKinsey Consulting. Second author, Adria Palou. Both of the first two authors have PhD from Cambridge. I like this paper a lot because they have a real problem. It's in a manufacturing environment. The assets are not the same. The machine tools are not the same, but they're doing the same thing. Some are old, some are not old. We cannot pool the data together because they're different. But there's not enough data on each individual unit separately to base a degradation process and make maintenance decisions. So instead, look at the title, a social network of collaborating industrial assets. In other words, how a component is degrading may influence the one next to it, or it may not. We don't know. So, but we collect the data and we let the machine learning or let the neural network make that decision. Now, they use this to feed into an optimization model as to how to dynamically adjust the workload and how to decide when to do preventive maintenance. So I'm using these as examples of what I see the future. Another one by excellent researcher, Murat Yildirim. You want to read some good papers. Integrated predictive analytics and optimization for opportunistic maintenance and operations. He has more recent papers. I need to update this. Another example, these are papers I wrote with Xiaoyan Zhu and various students, where we're doing a stochastic optimization and simultaneously optimizing design and maintenance, something I talked about at the very beginning, and I believe Professor Li is also interested in. Historically, design decisions were made, and it was a sequential decision. And once those were made, maintenance decisions were made. Watch my slide. We can make them simultaneously. Let me skip ahead. This is, we had this one paper with Jian Zhou, who's now a professor in Nanjing. Let me skip over this. Let me talk to you about my current plan. Coit, that's me, and co-authors XX and YY. I don't know. Date, I don't know. We have the system structure. We're going to solve a new model. We have our clustering model I showed you. I have objective function and constraint information from my combined optimization papers. Decision variables also. But now our optimization is like the Matizzi paper, where we're using machine learning and remaining useful life. So this is just an idea. I'm going to solve a two-stage optimization problem to get a design and maintenance. We're going to use machine learning to update. We're going to evaluate the predictive maintenance and continue to refine. We're going to compute, though, cost savings if we do change the design and possibly return. Now, let me end it this way. In China culture, do you know what a crystal ball is? A crystal ball, the legend is, if you can find a crystal ball and you can look into the crystal ball, you can see the future. Obviously, it's a myth. But it's something we've been told, a crystal ball. So here's how I'm concluding my talk. Professor Coit, that's me. My crystal ball. This is a paper written on the right. It's labeled 1996, but I don't think that's correct because it lists me as University of Pittsburgh. So that would have been before I joined Rutgers, so more likely written in 1994 or 1995. So in other words, 30 years ago. 30 years ago, the term machine learning had not been maybe computer scientists. I certainly never heard of it. However, look at this paper, solving the redundancy allocation problem using a combined neural network genetic algorithm approach. Here's the abstract. This paper presents a novel hybrid intelligent system, which uses the GA with a neural network to optimize a combinatorial engineering design problem. Okay, ... The neural network provides the objective function value for each candidate system. So I'm making the claim, prove me wrong, first ever use of machine learning for system reliability analysis. So I'm making that claim that that was my paper. And to be honest, I give my Alice Smith, my advisor, credit for this one because I think it's probably her idea. So let me just finish this. This is my last slide. I've gone exactly 2 hours, which is what I wanted to do. Future for system reliability optimization. Sometimes people will ask me, they say, Professor Coit, you've been studying this for 28, 30 years. Haven't you already solved every problem? And I can answer quite honestly, no, not at all. In fact, in one sense, we're just beginning. I really do feel that way, is that the number of problems that can still be solved is almost unlimited. And it's an exciting time with many new research challenges and opportunities. So machine learning, big data, sensor technologies, the evolution from a static to a dynamic problem is going to create all sorts of new problems. And furthermore, bullet 3, where we previously assumed known or assumed distributions, we don't have to do that as it becomes dynamic. The machine learning model can continually update. Maybe it's just an improvement of our current knowledge, but maybe things are shifting. Maybe the distributions are changing, and we can reflect that with the machine learning. And then my final bullet, and then I'm all done. We can customize or optimize for subsets of users. And so that concludes my talk. So I will stop sharing. I don't use this Teams too much. This isn't Teams, this is Tencent. Okay, is anybody there?
Okay, do anyone have questions to ask?
Okay, so let me say this. Professor Lee knows my email. I'd be glad to answer questions, talk anytime. So I'm finished.
Okay. If any student have questions, you can.
Okay.
Professor?
Oh.
Okay. All right. Nice meeting everyone. Oops. Okay, stop record. And Professor Lee, have a good day.
Hi, Professor Coit. Thank you very much.
Thank you very much.
Have a good day. Hope to see you soon.
Yes, I'll see you in Poland.
See you in Poland.
Okay, goodbye.
Goodbye.